Ali Ali Oxenfree. All right, so just trying to make sure I can hear. Okay. All right. So we'll figure out the collaborate momentarily another time. For right now, this is what I know, so I'm just gonna go with what I know. Ugh. Ugh. Gross. Okay. Anyway. All right. So yeah, we have right at about an hour, so we'll take some time. We'll take some time to make our way through. Let's see. Browser source. Yeah, we need to keep that active. Okay, what I can do. I'm gonna just let it be for now. Let me go like this and rename. This is iPad with, let's see, FaceTime and chat window. And then what I want to do, I would like to duplicate this. And what I'm going to do is this is going to be FaceTime and no chat window. And we can lock that one. Let's just suppress that. That's fine. That's fine. Press everything else. Okay. And then one other thing, we'll go over here to settings. I want that to be number 4. Here it is. 4. Okay. Okay. So we're back. Let me pull the chat window back up. Let me do a test real quick to see if I can get this chat. Let me see. Who all is here? Oh, time to find another stream. Okay. Let me go like this. Let me just refresh this whole thing. Let's copy the web, and then I'm going to say this is for calculus, UMC, spring 2020, 1.1, 4 ways to represent a function. Okay, function, yeah. I'm going to go like this, and then what I'm going to do, browser source. Okay, I know that's kind of long, but fine. Okay, so it should be there. I am showing that there are 3 people in attendance. Again, just try to be engaged. Just try to make your presence known. It's important. And I'll try to check the chat periodically to make sure we're like answering questions and things of that nature. And we will figure out the collaborate so that way you can get my attention and we can like go auditorily go back and forth and get people involved. But that just, I wasn't prepared for that. Like that's just me. And so I was like, but we'll get it worked out in the near future. I felt like I just posed for a meme. Anyway, okay, so let's take some time and let me see. We got a good amount of slides. We'll do the best we can. So we'll do the best we can with this calculus and try to keep it as simple as possible. Like that's the name of the game. Okay. And let's do like this. Boom. Ooh, okay. So let's see, how does this get, you coming up? What you doing? Come on. Come on. All right. I'm trying to let her get settled so I can focus. Stop. I'm gonna have to work with that. Yeah. Okay. Only thing is, I don't like how that looks, but I don't think I can do anything about it. All right, so we'll go with, let me see if I zoom in a little bit. I guess I don't like that either. Anyway, so chapter 1 is on functions and limits. Okay, so let's just kind of see how it evolves. So look, you gotta sit still. Thanks. Thank you. All right, so, oh my God, get down, go to bed, go to bed, go to bed, because you just dancing. Go to bed. Go to bed. Okay, sorry about that. All right, let's see. 4 ways to represent a function. Let's see what's going on here. So let's say it says that functions arise whenever one quantity depends on another. So this is, similar to like college algebra. Basically, you have like your set of inputs and then a set of outputs. And so this one asks us to consider the following situations. It says the area of a circle depends on the radius of the circle. So notice you have an independent variable versus a dependent variable. Dang, this is where we totally use the it is what it is. Exactly. Who is it is what it is. Like, I can't use that. I don't know who that is. So, that's no good for me as far as who that is. So yeah, it's probably a good idea to maybe make an alias YouTube account or something where you can be a little bit more professional. I might need to do the same thing, something that says Mr. Pfeiffer or whatever. But because if we have to, something that you're comfortable with people seeing on the web, because like if you have it is who it is, I don't know who that is. Anyway, let me see. So we have an independent variable, dependent variable. Let's see what else. So the rule that connects R and A is given by this equation. The area of a circle is going to be pi r squared, which each positive number R, there's associated one value of A. So remember, from college algebra, we said that, if a function passes the vertical line test. Okay. Sorry about that. Yeah, so the stream did go down. I noticed it. I stopped, and I don't really know how to troubleshoot that, so we just have to do the best we can. Let me see. So every y corresponds to exactly one x. So that's function notation. It says the human population of the world depends on the time t. The table gives the estimates of the world population. So we have the population as a function of t here. P of t, so the population is a function of t. So that means you can determine the population given any time for this function, right? So for instance, in the year 1950, the population was, what is that? 1,000 million billion. 2.5 billion? In millions, yeah, 2.5 billion. In 1950, yeah, 2,560,000. That was the human population of the world. But each value of the time t, there's a corresponding value of p, and we say that p is a function of t. So long story short, those rules for college algebra still hold, where it has to pass the vertical line test and all this other kind of stuff. Let me see. Oh, it looks like nobody's there. That's okay. It should be recording, so I'm gonna just kind of keep going. Probably when I stop this lecture, though, we'll probably stop if I make it. I mean, because this will go for a little while. So let's see. We have the cost C of mailing an envelope depends on its weight W. Although there is no simple formula that connects the weight and the cost, the post office has a rule for determining the cost when the weight is known. Right. The vertical acceleration A of the ground as measured by a seismograph during an earthquake is a function of the elapsed time t. So the acceleration is based on the time t, right? So let me see. So figure 1 shows a graph generated by a seismic activity during a Northridge earthquake that shook Los Angeles in 1994. For a given value of t, the graph provides a corresponding value of a. So based on the elapsed time, let me see, people in attendance. Okay. So based on the elapsed time, we can determine the, what is it, a? Oh, the ground acceleration, right? The way the ground is acceleration over time. So function f is a rule that assigns each value x, each element x in the set D exactly one element called f of x in the set E. So every element in the domain corresponds to exactly one element in the range. All right, you don't have the case where you have one x going to two different y's. What I do to kind of keep this straight, I always visualize or just imagine like a vertical line test. You know, it has to pass the vertical line test in order to be a function. So passing the vertical line test means you don't have where one x corresponds to two different y's, you know, where you have it stacked on top of each other or whatever. I'm watching the clock also. Let me see. So we usually consider functions for which the set D and E, the domain, or D and E, are the sets of real numbers. The set D is called the domain of the function. The number f of x is going to be the value of f at x, and is read f of x. This is going to be the range of f is going to be the set of all possible values f of x as x varies through the domain. So basically the range is the set of outputs. The domain is a set of inputs, so the range is a set of outputs. If you are live in the live chat, again, I ask that you make your presence known and try to use the live chat. So just to, you know, if you have questions, just go ahead and type, and I'll try to get to some of them here and there. Okay. You know, so just kind of stop me, just try to get my attention or whatever, and so we can try to get some questions answered. You can email me as well, because I'm kind of monitoring those as well. So maybe put in the subject, put calculus, so that it'll get my attention a little bit better. A symbol that represents an arbitrary number in the domain of a function is called an independent variable. Okay. So let's see. Oh, I wonder what else is there. Anyway. A symbol that represents a number in the range is called a dependent variable. In example A, for instance, R was an independent variable and A was a dependent variable. It's helpful to think of it as a machine, basically as a set of inputs and a set of outputs. So the function is like a machine. You have your x values as the input. Maybe if I go like this, it'll match. Nope. Let me go like this. Yeah, okay. Because sometimes the image is reversed, but it's not really reversed right now. But yeah, so our x is going to be a set of inputs. X is going to be a set of inputs that we pass through our function, and then the function is going to create a set of outputs as a result. Okay. So if x is in the domain of the function f, then when x enters the machine, it's accepted as an input, and the machine outputs f of x. Okay, I'm going to let that be. This is kind of belaboring the point. So this is what's also called, well, here it's called an arrow diagram. You might see me refer to this as a correspondence diagram. But basically, it's just a set, like the left set, let me see. Ooh, I wish somebody could tell me a color. Like, we're gonna get that audio working. But for right now, just for the sake of time, I'm just gonna choose a color at random, or try to. Okay, that's fine. I'm actually gonna fill that in. Okay. Let's go like this. So this is called an arrow diagram. So we have this set on the left. It's just a set of inputs, and then each element here is going to be output into our I think it's called like a codomain. Basically, our range are a set of outputs. So D is a mapping that passes through a function f. It goes, f is a mapping from D to E. Okay. So again, another way is called an arrow diagram in this figure. Each arrow connects an element of D to an element in E. The arrow indicates that f is associated with x, and f of a is associated with a, and so on. Okay. So this is called a set notation. The most common method for visualizing a function in this graph, if f is a function with domain D, then the graph is a set of these ordered pairs. So let's read this. This is like one of those major things that we need to kind of talk about. So this curly brackets just means the set of, right? So this is read in the following way. This is going to be the set of all ordered pairs x comma f of x such that this vertical bar means such that x, this is called is an element of or belongs to. We call it is an element of, but it means belongs to the set D. So again, this is red. This is the set of all ordered pairs x comma f of x such that x belongs to the set D. Okay? So hopefully you were able to kind of keep up with that. In other words, the graph of f consists of all points x comma y in the coordinate plane such that y equals f of x and x is in the domain of f. The graph of a function f gives us a useful picture of the behavior of the life history of a function. Let me see. I'm not seeing any live chat. Maybe it's not operational, but it should be because I think I updated it. Anyway, I'm going to let it be. So again, if you're on a live chat, just go ahead and make your presence known so that I can get a sense of who's here, who's who. This is for attendance. So we have to, we have to kind of check in for attendance. Okay. So since the y coordinate of any point on the graph y equals f of x, we can read the value f of x as being the height of the graph above the point x, right? So given any value x, let's go here. Given any value x, we can say that f of x is going to be the height above that value x, right? The y value. So f of 2 is going to be the height above when x is 2. So I'm just kind of following with the slides for right now. I think an example will be coming up shortly, hopefully. Okay, so I'm just going to piggyback. Let me see. So I'm going to piggyback off the way I explained this in college algebra as far as domain and range. So the domain, like if we're looking at this image, if we were to take this image and smush it onto the x-axis, that's going to be the domain. So the domain is the very left of the graph. So that might be the right side of the screen. I'm not sure if it's flipping or not. Let me see. I'm trying to see if I can see it. My left is this way. Smush. And it needs to go that way. Left. That's not the left. That's the right. Okay. So the domain is the very left of the graph to the very right. Just trying to match the image right, but maybe let me try it like this instead. So when we're looking at a graph, the very left to the very right is our domain, and then the very bottom to the very top is the range in a graphical sense. Okay, we're going to explore that. We're going to keep working it until it sinks in. Don't want to see the solution just yet. Okay, cool. This is exactly what I want. So what I'm going to do, I'm going to go ahead and add a page and see if we can work this one. Okay, so we have this example. It says the graph of a function is shown. Find the values f of 1 and f of 5, and then what's the domain and range? Okay. So f of 1, what does that mean? Oh, I see. Okay, I see you. Let's see. We got Ariana Edwards. Welcome. Your left is our right. Yeah, that's what I noticed. Yeah. Let me pause for a moment to go ahead and do attendance again. Since I know I got another person. I'll just do it at the end. Just we'll make sure that people get attendance credit. We kind of lax this week for right now. Okay, so looking at this one, it says what is the value of f of 1? So when x is 1, well, the height above 1 is whatever this is. 1, 2, 3. So let's see. Let's do what color is going to pop. Let's do like this, right? So when x is 1, the height above, we're talking about this guy here. All right, so then that y value, if that's 1, that's 2, so this is 3, right? So then from this image, f of 1 is going to be 3, and then when x is 5, 1, 2, 3, 4, 5 is here, right here. So then that means that f of 5, what's the height? Well, the height above that is 0, so f of 5 is 0. We didn't go up at all. So what's the domain? The very left. How far? Now, based on this image, the far left, again, the far left is over here, just based on this image. So I'm going to say from 0 up until 1, 2, 3, 4, 5, 6, 7. So I'm going to say the domain goes from 0 to 7. Now this is just me doing it off the fly. It goes from 0 to 7, and it looks like we include both of those x values. They're defined at those x values, so I'm gonna put them in square brackets. So then the range is gonna be the very bottom to the very top. How far down does this graph go? Right, so I think what we just saw, let me see if I can match those colors, was pink and green. I'll do blue and green. I'll do purple. Yeah, we'll do purple and green. Okay. So the domain is the very left. So on the x-axis, the x-axis goes basically from here to here. All right. Let me see. It goes from there to there. I guess that's fine. And then the range, the very bottom, it goes from here up to here. So this is the range from there to there. Okay. So then that range, the very bottom, what is that? -2, and the very top is 1, 2, 3, 4. Right? And then on the x-axis, again, the very left to the very right goes from here to here. So the very left, this goes from 0, and the very right is 1, 2, 3, 4, 5, 6, 7. Okay. And just to be consistent, the domain, we did that one in purple. Okay, what's on time? Man, time is going by so fast already. And then, so the range, nope. Let's go like this. We said our range went from -2 to 4. So just, if you have a question, just type it or email me, and I'll just periodically like kind of surface to see, if there are questions or whatever. Okay, so let's see, how do we do? We said that, and we don't need that page anymore. So we had that f of 1 is 3, and that's correct. Approximately 0.7 units below the x-axis, so we estimated it. Okay, well, I eyeballed it. I thought that they intentionally made that 0. Oh, I see what I did wrong. 5, right? When x is 5. Yeah, I totally got distracted. Dang on it. Okay. So let's do like this. So this one. So if you've taken one of my courses before, I do offer extra credit. Like if I walk away from a question and I get it wrong, I do offer extra credit for that. All right. So when x is 5, if I walk away from an example and it's wrong, you correct it and bring it to my attention, I offer extra credit for that. Okay. So I totally was distracted. And you're also gonna have to be patient with me because, again, I've been talking nonstop since about 10 a.m. So that's like 4 hours, and I'm going into like hour 6 or whatever. 10, yeah, give or take. So I'm more than likely going to make a good amount of mistakes here, but we just got to be patient and keep checking and, all this kind of jazz. So when x was 5, let's go back again. 1, 2, 3, 4, 5 is actually here. It's slightly below, and it's almost down to 1. So then that height here is approximately. So f of 5, approximately, we're going to say 0.7. Again, that's just an estimate. That's an estimate. So we got that one wrong, but, it's okay. Oh, and then negative, I still got it wrong. Ugh, I'm totally like out of it right now. Okay. So that's fine. And then we said 0 to 7 is fine, and -2 to 4 was good. Okay. So the other one gave us a little bit of a hard time. What time? Okay. All right. So I'm watching the clock. I know that we have about 30 minutes remaining. Okay. So we'll do the best we can with this section. Whatever we don't finish together, you're going to be responsible for. I know you may or may not have your materials. We're just going to have to be in communication until we get everything uploaded. Again, my intent is to gain full access to Cengage because I'm under the impression that we can actually get full access for free because of all the corona. So just kind of got to give me a little bit of time, and we're going to do it that way. Okay. So let's keep going. So again, there are four possible ways to represent a function: verbally by description in words, okay, numerically by a table of values, so we can make a table, visually by a graph, and algebraically by an explicit formula. Okay. So let's look at this example. Don't want to see the solution just yet. It's okay. When you turn on a hot water faucet, the temperature T of the water depends on how long the water has been running. Draw a rough graph of T as a function of the time that has elapsed since the faucets were turned on. So if you think about, like, okay, it says draw a rough graph of the temperature as a function of time. So capital T is the temperature, lowercase t is the time, right? So I'm just going to do a rough sketch on my own of what I think this means. All right. So usually our independent variable goes on the x-axis on the bottom. That's going to be the time. The temperature depends on the time, right? So if we think about, like the temperature based on how long the faucet's been running, when you first, like if you turn on the hot water, when you first turn it on, it may or may not be hot. And then what should happen? You would anticipate like the temperature to rise, and it eventually should reach a plateau. And then eventually you would think that it would come back down. I think you could anticipate like some kind of image like this if you were observing the temperature as over time, right? So let's see, how do we do? The initial temperature of the running is close to room temperature because the water has been sitting in the pipes. When the water from the hot water tank starts flowing to the faucet, the temperature increases quickly. In the next phase, the temperature is constant at the temperature as the heated water in the tank. So we get something like this. And that's similar to what we did, So we're going to kind of let that be for right now. So it says the graph of a function is a curve in the xy plane, okay? But the question arises, which curves in the xy plane are graphs of functions, okay? So we did talk about something like that in college algebra and in pre-cal. How do we determine if a graph is a function? It has to pass I'm going to pause for a moment for you to kind of think about that. Given a graph, how do we tell whether the graph is or is not a function? It has to pass the vertical line test right there on the screen. Reading is fundamental, Lord knows I have my struggles. Vertical line test, but it's there, okay? Figure 1.3, right? So if we look at figure A, no matter where we draw a vertical line, it's only going to touch our graph once, right? So in this figure A, no matter where we put that pink vertical line, it's only going to touch it once. Versus in figure B, you can find a location to draw a vertical line and it touches the graph more than once. So this is an example of a graph that is not a function, right? Because the second one fails the vertical line test. Each vertical line x equals a intersects a curve intersects a curve only once. But if a line x equals a intersects the curve twice or more, then the curve is not a function. Basically talking about the vertical line test. So for example, say we had the parabola x equals y squared minus 2. Yeah. So let's see. This figure is not the graph of a function x because you can see that you can draw a vertical line and it touches the graph more than once, right? So this is not a function. Not too bad. Notice that this equation implies, now, say we had this equation by itself and we wanted to get a sense of the graph. Keep in mind, we can use graphing calculators. But most of our graphing calculators allow us to input y equals something. This is x equals something. So say we wanted to graph this, there's a couple of ways. What I would do is we could solve for y. So if we solve for y, if we add 2 to both sides, and when we take the square root, we have to include a symbol. That symbol is going to be plus or minus. So we're going to have plus or minus the square root of x plus 2. Okay, so we talked about in college algebra on how to graph square root function. Okay, so we want the top half and the bottom half. Okay. So then when we put those two pieces together, we essentially get an image like this, and it fails the vertical line test. Okay. I'm gonna let those be. So we observed that if we reverse the roles of x and y, then the equation x equals h comma y does define x as a function of y, with y as the independent variable and x as the dependent variable. And the parabola now appears as the graph of the function h, which is not there. Where's h? Anyway. Sorry. All right. So what do we mean by a piecewise defined function? A piecewise defined function. So let's look at this example. A function is defined here and it asks us to do this evaluation. So let's kind of go like this. All right. So we don't want to see the solution. And I'm going to mute this. That's okay. Actually, let's go like this. Nope. Nope. Let's just do this one. All right. So we have evaluate f of -2, f of -1, f of 0, and sketch the graph. So to evaluate when x is -2, we have to ask ourselves, are we going to use line 1 or are we going to use line 2? Well, if x is -2, -2 is less than -1, so we're going to use line 1. So that means if we do f of -2, that's going to be 1 minus a -2, which should be 3. If we do f of -1, again, we have to ask ourselves, do we use line 1 or line 2? Well, if x is equal to -1, that means we're going to use line 1. So this is going to be 1 minus -1, and that one should be 2. Okay, if we're going to do f of 0, sorry about that. If we're going to do f of 0, 0 is bigger than -1, so we're going to use the second line, and that's going to give us 0 squared, which is 0. All right. So then to sketch this, the left-hand side is going to be the straight line 1 minus x, so it has a negative slope and a y-intercept of 1. And then the right-hand side, we're going to do the right-hand side of x squared, right? So basically you graph those two by themselves and then erase the part that you don't need and you'll get this kind of image. Okay. If this example is not clear, try to get my attention. Let me bring back up the chat window. So if this kind of thing is not clear, just get my attention, or you can email me and we can talk about it separate, and I could do a dedicated YouTube video doing that by hand, right? If needed. Okay, let's kind of keep going. Okay, so for the next example of a piecewise defined function is the absolute value function. Again, can we recall what is the absolute value? For instance, what is the absolute value of 13? What's the absolute value of 1/2? What's the absolute value of -50,000? What's the absolute value of -2? What's the absolute value of 0? Absolute value is the positive distance away from 0, and the absolute value of 0 is 0. All right? So absolute value is the positive distance away from 0. Man, see, this is nice. I don't like, I ain't gonna lie. So, I'll be tired after teaching. I've been talking nonstop for like 6 hours, and like I would be exhausted. And then, for me to drive home, that was like almost an hour, and then you want to factor in traffic, so then like throw more time on that. And so I was just like, oh my God, it's so sleepy. But now, I'm at home. So once we're officially done, I'm gonna do the best I can to honor the time and kind of do that whole thing. As soon as I shut all this stuff down, boosh, like recharge my batteries, man. So, and again, I am available. Just email me. If anything is not clear, if you need help, just email me, and I can do dedicated YouTube videos for any of this stuff. Okay. So, let's see. So we know that the absolute value of a number A is going to be, you see the symbol here, absolute value of A is the positive distance from A to 0 on the real number line. Distances are always positive or 0. So we have that the absolute value of A is always greater than or equal to 0 for every number. Okay. And we see some examples of absolute value of different numbers. How do we graph it? Uh, so with that question, if you could find an example in the homework. So the best way to make use of my services is to give me specific examples, right? I know we've seen this graph already, so I don't really want to do this one because we've seen the image. But in your homework, as you're practicing, if it asks you to graph a piecewise and you still can't get it, then I would rather do something like that. So that way, I'm not being led by the answer. I'm not catering to the answer. But we'll definitely explore that. But basically, to graph a piecewise function, all that we do. So to graph a piecewise, so these are essentially two graphs on one plane. The first graph is the first line. It's just 1 minus x. It's a straight line because the highest exponent is 1. It has a negative slope because the leading coefficient is negative. And the y-intercept is positive 1. All right, so that's just a straight line. But that we only keep the part where x is less than or equal to negative 1. So we're going to keep the left-hand part and erase the right-hand part of that graph. And that one gets a closed-in circle because it has a bar. The second graph is just going to be y equals x squared, just a regular parabola like normal. But we keep the part where x is greater than negative 1. So we're going to keep the right-hand side, erase the left-hand side of that graph, and the endpoint gets an open circle because there's no bar under the inequality for the second one. All right. So once you put those ideas together, we get an image like this. Okay. And again, if that's not clear, what we can do is, as you're going through the homework, reach out to me and say, hey, Mr. Pfeiffer, I'm working this section, this question. Here's an example of a piecewise. Do you mind graphing this by hand? And I'll do it. That's what I'll do. And I'll make a dedicated YouTube video. And especially once we get the audio working, then we can kind of go back and forth. You know what I mean? What's the clock? We got 20 minutes. So the next example of a piecewise function, yeah, we just did that. So in general, the absolute value of a is a if a is positive, and the absolute value of a is going to be negative a if a is negative. For instance, say we did the absolute value of negative 3. If we apply this rule, we're going to use the second line. It's going to become negative 3, which becomes positive 3, right? So if a is greater than or equal to 0, then it's just going to be a. If a is strictly less than 0, then it's going to be negative of whatever that number is. Okay? Double negative is positive. We're actually sketch the graph of the absolute function, absolute value of x, right? Absolute value of x, again, is really just a graph of y equals x, but if x is less than or equal to 0, those negative y's become positive. So then the absolute value function is essentially, you could actually make a table. So choose some x values, choose some negative x values, choose 0, choose some positives, plot them, and eventually you'll get the straight v. You'll get this v like this. All right. So it does take practice to graph these by hand, okay? But you can do it. And just keep asking questions. Your job is to ask the questions, I'll answer them. All right, let's look at this one. Watching the clock. We're doing good as far as pace. We're getting down to about 15 minutes. We'll probably go for like another 10 minutes, or if we finish, so we're almost there. So in example C at the beginning of the section, we consider the cost C of W of mailing a large envelope with a weight W. In effect, this is a piecewise defined function because from the table shown on the right, we have, let me see. If the weight is between 0 to 1 ounces, is 98 cents. Between 1 to 2 ounces is 1.19, so on and so on. Yeah. So an independent variable is our W, and that's telling us the weight, and then we have the costs, the associated costs of those different weights. So what this is called a piecewise function because the outputs collapse to like specific, usually, it just collapses. It kind of collapses all of the answer choices, all the results on a range, right? So you see how the x's have they go from like 0 to 1, 1 to 2, or whatever. But then any weight that goes from 0 to 1 is gonna cost you 98 cents. So all the way from 0 to 1 is 98 cents. Then the next one, so basically you just graph each one separately. All of these are horizontal flat lines because there's no x value in the 98 cents or the 119 and all that. There's no variable. Those are all just flat functions. So this is what's called a piecewise step function. It's called a piecewise step function. Okay. Let's see what else we're looking like. So symmetry. Let me see the clock. I want to go for about another 10 minutes or so. Symmetry, let's see. So if a function f satisfies the condition that f of negative x equals f of x for every x in the domain, then f is called an even function. So that's a definition of a function being even. A function being even means that when we replace x with negative x, we get back the original. Another way you can visualize the even function is that it has y-axis symmetry. Whenever we have x and negative x, they both map to the same y value. This is a function. This is an example of a function being even. And even the official definition for even means this thing here: f of negative x equals f of x. In a graphical sense, a function being even means that it's symmetric about the y-axis. So if we were to take this image and fold it in half along the y-axis, then the two halves are going to match up. So even, y-axis symmetry, f of negative x equals f of x, these all mean the same thing. Okay. So the same way we have an even function, we also have what's called an odd function. An odd function, the definition of an odd function is whenever we do f of negative x, we also have negative f of x. All right. So an odd function has origin symmetry, not x-axis symmetry, but origin symmetry. Origin symmetry basically is like whenever we have x comma y, we also have negative x comma negative y. So it's like in a graphical sense, it's like if you put your thumb on the origin and if you cut it in half horizontally, like right in through the origin, if you put your thumb on the origin and take that top half and rotate it 180 degrees, the top half is going to match the bottom half. That's, to me, that's a visual sense of what we mean by an odd function. See, so again, with this image, if you put your thumb on the origin and take the top half and rotate it 180 degrees, the two halves are going to match up. To me, an odd symmetry, origin symmetry to me is like rotational symmetry. That's just the way that I see that one. But whenever we have x comma y, we also have negative x comma negative y. Okay. Whew. Give me just a moment. Ooh. Okay. Ooh, that was a good stretch. Oh, I'm about to be out. So part of the reason I'm so tired, I did go running. Before work, I went running like from 6 to 8. That was fantastic. But I'm yet holding on, but barely. Okay. And even before that, I was kind of just like wired, but that's neither here nor there. Okay, so determine whether each of the following functions is even, odd, or neither. Okay. So yeah, let's screenshot this and let's get some inspiration. Don't want to see the answer though. Not just yet. So we're going to get a copy and let's see how to calculate if this is even, odd, or neither. All right. I think I see it there. Let's add a page. Awesome. So let's give this one a go. And let's go paper, grid paper. Oh, we're going to have to wrap up. We got time for maybe one more example after this. Let's see. So, even by definition means that when we do f of negative x, we get back the original. Odd means when we do f of negative x, we get negative times the original. Okay, so it's like the negative kind of gets factored out. But let's see this in action. Okay, and actually... Just a moment. I'm just kind of working on my spacing a little bit. That looks good. Okay. So let's apply these. Let's see these in action. So say we're doing example 11a. Ella, that's funny. Example 11a. All right. Xella. Anyway. So if our function is f of x equals x to the 5th plus x, all we do, we're going to do f of negative x. So we got a negative x, negative x, negative x, okay? Now, if we have negative x to the power of 5 in this fashion, if we have 5 negatives, will our final answer be positive or negative? If we ultimately have an odd number of negatives, will our final answer be positive or negative? Our final answer will be negative, right? So it's going to be negative x to the 5th. Again, and the next one we have an odd number of negatives, so that's going to finish as minus this. So then notice, with this, we can actually factor out that negative. So we can get this. Okay. Is it safe to say that this is actually just negative times the original? And this is the definition of a function being odd. Okay. So we replaced the x with negative x. We simplified. We ended up getting negative times f of x. So then that means that this function is odd. That's the definition of a function being odd. Oh, let's go ahead and do b. 11b. We have g of x equals 1 minus x to the 4. Okay? So then if we do g of negative x, 1 minus negative x to the 4. Negative x, negative x. And that's totally not the color I thought I had chosen. Oh, I guess it clicked already. Okay. What time is it? Okay, we're about to wrap up. I see the time. So now in this example, if we have a negative x to the power of 4, notice we have an even number of negatives. So that means that that term ultimately is going to be positive, and we're going to get 1 minus x to the 4. And is that the original? This is actually the original. So this is what we mean by a function being even. This is what we mean by a function being odd. All right, I'm going to let that be for now. Let's see. I guess we could do that one. So if we did C, example 11C, we have h of x equals 2x minus x squared, right? Let me cut, and I think I need to add a page. I'm totally about to pass out. I'm so sleepy. I haven't eaten. Like, I just been sitting here. I'm like, oh my God, this is intense. But it's all good. Let's see. Oh, I want to paste. And next I'm going to paste it on the next page, okay? So we want to do a test for even, odd, or neither. So that means we're going to do h of negative x is going to be 2 times negative x minus negative x squared. I'm trying to choose a color I haven't used. Negative x, negative x, negative x. Okay. Oof. So let's work it out. All right. So 2 times negative x is negative 2x. Negative x squared becomes positive times another negative is going to be negative x squared. If we factor out the negative, we're going to get negative times 2x plus x squared. Is this negative times the original? No. Is this just the original? No. So then this is an example of is neither even nor odd. Okay. All right, let me try to wrap this up. We're actually almost done. We'll kind of scan real quick. So we got what? Odd and then even and then neither. Odd, even, and then neither. So part A is an example of origin symmetry. Part B is an example of y-axis symmetry. And part C is an example of no symmetry. So the simple explanation for what we mean by increasing, decreasing, and constant. Increasing means as we trace the graph from the left to the right, so I guess to match the image, from the left to the right, it's going to go up. That's what we mean by increasing. Oh, I thought I had, oh no. I thought I had my thing on. How did that get through? That's deep. Anyway, I had to call her back. Okay, I got a plan for that. I didn't realize it was going to get through, but that's okay. Oh yeah, so as we trace this graph from the left to the right, it goes up. As we trace the graph from that's what we mean by increasing. As we trace the graph from the left to the right and it goes down, that's what we mean by decreasing. And as we trace the graph, let me see. Let's just do. I guess I have to do this one too. I guess that'll be wise. Where is it? Here it is. Okay. So increasing means as we trace the graph left to right, it goes up. Decreasing means as we trace the graph left to right, it goes down. And constant means as we trace the graph left to right, it stays flat. Okay. That's essentially what this means. That's a simple explanation. So for instance, this graph here, as we trace it left to right, and this first is going down. So it's decreasing based on the domain, it's decreasing from negative infinity to 0. And then it's increasing from 0 to infinity. Now, another text I looked at said that you pretty much always use open parentheses. But see, they have square parentheses here. So, yeah. I'm not going to worry about that too much. Oh, was that it? That was it. Okay. So let me go ahead and load a copy of these notes. Sorry. My voice is gone. Oh, I'm glad I did that. Let's go here to paper. So I'm going to load a copy into Box, and you should be able to access it from the Moodle page. Let me see. That's this one. Supports, app stats, calculus. What? Why are there two of those? I had to fix that. If we go to the notes, I'm going to export there. Okay. So any notes that you saw me taking, I'm going to load a copy into Box, and you should be able to access it on our Moodle page. If not, just contact me and I'll update it. So once this bar finishes loading, you'll receive a copy of the notes that you saw me doing. Just give it a moment. Okay, so with that, I think we're gonna go ahead and end the session here. Let me think about it. So we will figure out. So a couple of things that we need to do. So one, I want to say thank you all for getting in attendance. You guys did great. I'll make sure that you get your attendance credit. We're gonna be in contact for getting access to the online. It's not Pearson. It's something called Cengage. So you have to give me some time for that to get that set up. But I had to call the representative and all this stuff. But we're gonna get that going. Just do the best you can for what you have, whatever you have right now, because I know you probably don't have your text either. So, I'll make sure to get you access to that as soon as possible. But on that note, we're gonna end the session here. And from one beautiful mind to another, enjoy the rest of your day. Peace.